Hello and welcome to the fifth video of the FP3 chapter, Vectors. Start a question on the screen. If you have time, pause the video, give this a go. Determine the equation of the line that goes through these 2 points, and we have to write it in 3 different forms. So the key point here is that we need to find a position vector of a point on the line and the direction vector of the line. So the position vector of a point, we could choose P or Q. I'm going to choose P. And the position vector is one of them minus the other one. It doesn't matter which way round. And we get minus 6, 2, and 4. From here, we can use this information to write our equations. Perhaps the easiest one is this one. So we put in the position vector for A and the direction vector. Different form, we could do R cross B is equal to A cross B. And then we would do this calculation A cross B, which gives us 4 minus 2, 6 minus 16, and 8 minus 6. So here is our second form. The third form, Cartesian form, we start from r minus a is equal to lambda b. And we put in x, y, z for r, the point we know for a, and b. And then if you put the two vectors on the left together and you equate your coefficients, you end up with x minus 4 divided by minus 6, y minus 1 divided by 2, and z plus 1 divided by 4, all equal lambda. So these three are different forms for the same line. Okay, in this video we're going to talk about planes and the different vector equations of a plane. Just like a line, there are some key characteristics, and once you know those you can write the different forms, but there are different forms depending on the context of your question. But first of all, what is a plane? A plane is a two-dimensional surface like this. We often call these capital pi. So if you see capital pi, assume it's talking about a plane. And then just like with a line, we need to know where this is in space. So from a fixed point origin here, we need to be able to get to the plane. Any point on the plane will do that. So if this is point A, then the position vector little a takes us to the plane. And then we could talk about moving inside the plane to any other point R with position vector little r, and r minus a is a vector inside the plane. And as this point moves anywhere in the plane, that is still true. R minus a is still a vector inside the plane. But a key point here is to note the normal. The perpendicular to a vector in the plane, r minus a, is here. And no matter where r moves, the vector r minus a will change. It will always be in the plane, but it will be different. But the perpendicular vector to that will always be this direction. So for the whole plane, this n is the normal. And that is a very important point, because if it's true for all vectors within the plane that n is perpendicular to them, that becomes a defining characteristic of the plane. So with a line, we need the position vector and the direction vector of the line. With a plane, we need the position vector of a point and the normal to the plane in order to define it completely. So we can write the equation of a plane in three different ways. The first one here, the scalar product form, is taking that idea that r minus a, this vector here, and n are perpendicular, and we know that two vectors that are perpendicular, the dot product between them must be 0. So if we know the point on the plane A, the general point r, we get this vector r minus a, and if the normal must be perpendicular to that, we can write this. And it's more commonly expanded, rearranged to this. And as with the equation of a line that was in a similar format, if you've got something on the right hand side and you know what a is and you know what n is, you should do that dot product, and your answer for the scalar product form of a plane will be something like this, where p is the scalar answer of a dot n. So that's the first form. Quick example of that: a point with position vector this lies on a plane, and the vector this is perpendicular to the plane. This is a very quick and easy question because here they've given us a position vector of a point on the plane, and here they've given us the normal perpendicular to the plane. So we've got r dot n is equal to a dot n, and all we need to do is put these straight in. 3, 1, minus 1, 2, 3, minus 5, 3, 1, minus 1. And then, as I said, if you know what these are, you should go ahead and do the dot product. So we've got 6 plus 3 plus 5 gives us 14. And there is the equation of our plane. So the second option is called the Cartesian form, and that goes straight out of this. This is our starting point, and we just say, if we know what n is, r is the general point x, y, z, go ahead and put them in, do the dot product as normal, and where n1, n2, n3, and p are numbers that you will know in terms of finding the equation of the plane, they are numbers to find, x, y, z will be variables. You can then just rearrange that to give this, which is the Cartesian form. So a quick example of that. Find in the form r dot n equals p, so we've got to do this bit first. An equation of the plane which contains the line L, and that has the equation this, and the point with position vector a here. And then a tag on, find also the Cartesian form of the equation. So we have a plane, and inside the plane we're given the equation of a line. We're also given the position vector of a point. Now if you wanted to convince yourself that the point is not on the line, just put this into here and see if you can find a lambda that will make that true, and if you try and do that, there is no lambda that will make that true. So the point is not on the line. But for the equation of the plane, we need a, and we also need the normal. This time they have not told us the normal to the plane. So we're going to have to figure that out. How do we do that? We use the cross product that we've talked about previously, because the cross product gives us the perpendicular vector to two non-parallel vectors. And in the plane we have one vector here, the direction vector, -1, 2, -1. So long as we can find a second non-parallel vector, then we can cross those two to find the normal. And we can use the point on the line given here, 3, 5, -2, and the point that's not on the line that's given to us, and we can make a second vector in the plane here. Okay, let me do that first. So we've got, let's call this B, and then I'm going to call the second one C, and that will be the difference between 3, 5, minus 2, the point on the line, and the other point we're given, 4, 3, 1. So we've got minus 1, 2, and minus 3. So this is a second vector in the plane that is not parallel to B. So I can find B cross C, and that will equal the normal. And this is a very standard approach. Two vectors in the plane, cross them to get the normal. So we've got minus 1, 2, minus 1, crossed with minus 1, 2, minus 3, and that will give us minus 6 minus minus 2, 1 minus 3, we've got minus 2 minus minus 2. So here is the normal for the plane. Now we have everything we need. We've got A and we've got N. We can put this into our equation. R dot N is equal to A dot N. We can do that dot product. That gives us minus 16 minus 6 plus 0. So R dot minus 4 minus 2, 0 is equal to minus 22. And that answers the first part in the form R dot N equals P. Now the second bit, find also the Cartesian form of the equation, is much easier. Now that we've got this, this is an easy add-on because R is the same as x, y, z. And all I have to do is the dot product here. That gives us minus 4x minus 2y plus 0z plus 22 equals 0. And here is the Cartesian form of the equation of the plane. Okay, there is one more form, and that is called the vector form. And it uses the ideas that we had in the previous example there, that we could find two non-parallel vectors in the plane in order to find the normal by crossing B and C. But instead of doing that, we could just use those as a sort of a Cartesian coordinate grid, like an x and y axis on a graph. So long as they're not parallel, they don't need to be perpendicular to each other to get us anywhere in the plane. So if I go from O along A to the plane, then some multiple of B in this direction and some multiple of C in this direction, that's enough to get me anywhere on that plane, so long as these two are not parallel. And we don't need to do anything with this. This is it. Position vector of R is equal to position vector of A plus some multiple of a vector in the plane plus some multiple, notice a different multiple potentially, of a non-parallel vector in the plane. So we have the scalar product form, which will be this one, and you'll probably find the answer written like this by the time you've finished. Cartesian form here, which comes straight out of this. A vector form here, which uses the two non-parallel vectors. And these three are using more or less the same information. The position vector of a point on the plane A, to get to the plane from the origin, that fixes where the plane is in space. And then two non-parallel vectors in the plane, either because you're going to use them like this, or because you're going to cross them in order to find the normal. Obviously, if you already know the normal, then you don't need these as well, if you are just going to write this or this. And if you needed to, you could work backwards from the normal to these two vectors, because every vector in the plane is perpendicular to the normal, so you know that n dot b must equal 0 and n dot c must also equal 0. And if you know n and you know it has to equal 0, it's quite easy to choose vectors for b and c, just making sure they're not parallel to each other to make this true. So any one of these forms you can use to find the other two. Final example then. A plane pi passes through the points this. Find the equation of the plane pi in the form this. Also find the Cartesian equation of the same plane. So we're doing pretty much everything here. So our plane contains 3 points. We can use any one of them to get us from the origin to the plane. I'll use A just to keep the notation the same. And then we need two vectors inside the plane. So from A to B, let's say, and from A to C. It doesn't need to be these two, but these are the two I'm going to use. So we've got A, 2, 2, minus 1. If I call this P and Q, then I can use little b to be a vector in the plane, and that will be P minus A. That will equal 1, 0, 0. That's a nice vector. And then C, a non-parallel vector in the plane, will be Q minus A. And that will be 2, 1, 6. So I've got A, B, and C. Now I can write the plane equation in the form they want. 2, 2, minus 1, plus some magnitude, some multiple of 1, 0, 0, plus some multiple of 2, 1, 6. And that is the first part of the question answered. To find the Cartesian equation of the same plane, what I'm going to do is go through r dot n equals a dot n, and then replace r with x, y, z. So I need to know what is n. And n is the cross product of two non-parallel vectors in the plane. And those zeros make this a little bit easier. First element is 0, minus 6, and 1. So r dot 0 minus 6, 1 is equal to 2, 2 minus 1 dot 0 minus 6, 1. And that is equal to 0, minus 12, minus 1, minus 13. And r is x, y, z. So the equation of my plane is 0x minus 6y plus z plus 13 equals 0. And this is the Cartesian equation of the plane. I hope that's enough for you to do the questions from exercise 5e, and maybe I'll see you in the next video.